Okay, let me check the volume. And perfect. I'm gonna solve the problem here. The equilibrium constant of Kp. This is for general equilibrium. Uh, for the formation of of nitric oxide NO in an automobile engine at 537 degrees Celsius is 4.5 times 10 to the negative 11. So we got that the Kp, okay, is 4.5 times 10 to the negative 11. Okay, and the reaction of the formation of N2, NO would be N2 plus, you want to go somewhere? O2 in equilibrium with 2NO gas. Okay, calculate the partial pressure. Are you okay? Calculate the partial pressure of NO. Okay, so they're asking for the partial pressure of NO under this condition if the partial pressure of nitrogen and oxygen are the partial pressure of nitrogen are 3.0 atmosphere, okay, and partial pressure of oxygen is 0.012 atmosphere. Okay, so these are but it doesn't say that it's initial, okay, because it's under these conditions, and that's the Kp. They're giving you the Kp. So the first thing, write the expression for Kp, and it's the products over the reactants. So you got NO, the partial pressure. It's not the concentration. Uh, so we got here is the partial pressure of NO. Now is to the square because the coefficient is 2 divided by the partial pressure of N2 multiplied by the partial pressure of O2. Okay, 1 and 1 coefficients. So we need to find out the P of NO. So to the square, you bring this to the top, and it's going to be Kp multiplied by partial pressure of N2 multiplied by partial pressure of O2. So partial pressure of NO, we get the square root on both sides, and it's gonna be, okay, square root of Kp by Pn2 by PO2. Okay, because if you get the square root on the left side and on the right, you eliminate the 2. So the partial pressure of NO is equal to, let's look at the values we have to plug them in. The formula 3.0 by 0.02 or 12. 3.00 by, and this is all square root, by 0.012 by 4.5 times 10 to the negative 11. This is going to give you that the partial pressure of NO is equal, if you multiply all this and get the square root, is 1.3 times 10 to the negative 6 atmosphere. Now, on the second part, the problem says repeat the calculation for atmosphere condition in which the partial pressure of nitrogen and oxygen are 0.78 and 0.21 and the temperature 25 degrees Celsius. Okay, so we do the same thing and we got the new values is 0.78 the nitrogen and 0.21 the oxygen. Okay, so the partial pressure of N2 is 0.78 atmosphere and the partial pressure of O2 would be 0.21. Yeah. So this would be 0.21 atmosphere. Now at a new temperature, because it says clearly here that the temperature would decrease from 537 Celsius to 25 Celsius. And but the Kp changes, of course, and it's 4.0 times 10 to the negative 31. So the partial pressure of NO, okay, let's write the Kp. Kp equals 4.0 times 10 to the negative 31. You see how the Kp decrease? Okay, and it's gonna be this is gonna be the same thing we did in part A, but with the new data. 4.0 times 10 to the negative 31, okay, multiply by 0.78 multiply by 0.21, and it gives you 2.6 times 10 to the negative 16 atmosphere. So the next question is the reaction endo or exothermic? And what do we think? How do we know? Well, first of all, the K decreases with a decrease in temperature. And watch what happens to the equilibrium. The equilibrium will shift to the left. Okay? And shift to the left because the production of product is, look at the two quantities. Here is 1/3 by 10 to the minus 6, and this is 2.6 times 10 to the negative 16. Okay? So that means, and we saw here that the Kp decrease here. So it's 4.5 times 10 to the negative 11 to 4.0 times 10 to the negative 31. So that means that the Kp decreases, okay, with a decrease in temperature. Okay, so what is it, exo or endo? And if it's exothermic, let's say the reaction, okay, you have the heat here, okay? So that means that if you decrease the heat, the reaction will go to the right, okay? If this is endo, right, if you decrease the heat, right, the reaction would be to the left, okay? Because you're decreasing part of the reactant, if we put that. So if the temperature, okay, if the Kp decreases with lowering the temperature, no more will be formed and the equilibrium, if the Kp increases with a decreasing temperature, in a decreasing temperature, okay, so for studying this, okay, let me do this again to make it more clear. Mhm. So if the reaction, let's say you got here, okay, A plus B in equilibrium with C, okay, if it's endothermic, the heat would be on this side, yeah, as a reactant side. So if you increase the temperature in an endothermic reaction, the Kp is going to increase. The Kp increase because it's going to shift to the right, right, and it's going to produce more C. Okay. Now, if you decrease the temperature and it's endothermic, right, the Kp is going to be is going to get lower because it's Le Chatelier principle. So Kp will decrease too, okay, and is goes to the left, okay, shifts to the left, and it's going to be less C will be produced. Okay, so we have the example here. Less reactant is going to be produced. The Kp, instead of 4.3 by 10 to the minus 4.5 by 10 to the minus 11, we're talking about a Kp of 4.0 times 10 to the negative 31. So you see in this case, and the second temperature is lower than the first, much lower. So in this case, it's endothermic because we reduce the temperature and the Kp decrease and the amount of product decreased too. So, and let's do the other one just in case when it's exo. A plus B gives me C, and let's say it's exo, so you put the heat on the right side. So what happens if you increase the temperature here? Okay, temperature. You increase the temperature. So it's going to go to the left, because, and Kp would be decreased. Because if heat is here and you increase it, it will go shift to the left, okay? And you would have less product. Now, if the temperature decreases, right, what is going to happen with the Kp in that? If the temperature decreases, Kp is going to increase. Why? Because it's shifting to the right, producing more C. Let's check the volume again. Perfect. Okay, so now let's do the next problem. Okay. Okay, we have considered the following reaction system, and it's gonna be 2NO plus Cl2 and 2NoCl. What combination of temperature and pressure, high or low, would maximize the yield of the NoCl, the product? Now, why are they giving me the enthalpy of formation? Because you're going to find the enthalpy of formation per mole of reactant to know if it's exo or endo. So the first step is using enthalpy of formation, standard enthalpy of formation. You're going to find out the enthalpy of the chemical reaction. And that is going to tell you if it's exo and endo, or endo. And that is used to determine the shift or direction of the equilibrium, the shift when I change temperature. What is the temperature change? The other thing that you have to do is determine the difference of moles between the reactants and product. And you have 2 minus delta N. Delta N would be 2 moles coefficient of the products minus 2 plus 1. So it's going to be 2 minus 3, negative 1. Okay, the third step was determine delta N. And the fourth is, with the increase or decrease in pressure, we study the effects of pressure effects. Okay, let's go and get started. Let's calculate the enthalpy of the chemical reaction. And it's the enthalpy, standard enthalpy of the chemical reaction would be equal to, don't forget, is the sum of the enthalpy of formation of the product thing minus the sum things of the enthalpy of formation of the reactants. Okay, so now let's look at each one and make the calculation. You have here the enthalpy of formation of NaCl, of NO, and CO2. And don't forget to multiply by the number of moles, because at the end is the enthalpy of formation per mole of reactant. So we got, okay, the NaCl is the product, right? And you get 2 moles of that. So you're going to multiply by 2, okay, moles multiply by enthalpy of formation of NaCl, 51.7 kilojoules per mole. Okay, you cancel it out, of course, and at the end it's going to give you moles per, it's going to give you joules per, kilojoules per mole of reactant. And then you got negative, you can open the brackets, okay, and you're going to have the enthalpy of formation of NO, okay. On the left side as reactant you have NO, okay, twice NO and 1 chlorine. So it's going to be 2 moles of the NO, which is 90.4 kilojoules per mole. Okay, and then we have the chlorine, which you have 0, and any substance, if you remember, okay, in uncombined in the state, like when they're not forming a compound uncombined, is 0. The enthalpy of formation of chlorine is 0. Okay, so that is going to give us this minus 2 by 90 is going to give us a total of, the enthalpy of a chemical reaction would be minus 74.4 kilojoules per mole of reactant. Okay, so you got here, okay, let's look at now at the combination. You got that the number of moles, the delta N is negative, means that the product has less moles. And then you got that the enthalpy is negative. So if you increase the pressure, that's the condition, what combination? Okay, increase the pressure, okay, the reaction would go to the least amount of moles. So meaning that you have least amount of moles on the products. So if you increase the pressure, it wants to the right. That's what we want, because it said maximize the yield. of the product. So meaning that it's going to move more. You're interested in see how the effect moves the equation. You want to see the shift to the right as a consequences. So then the heat is you add the heat. Where was the heat? If it's X, so the heat would be on this side, right? So what you have to do too, okay, to get more products to go to the right. If it's X, so you're gonna need to re lower the temperature, which is reduce the heat, and it will take me to the right. So what combination is this one? Low low pressure. No, I'm sorry. High pressure and low temperature. Yeah, high pressure and low temperature. I don't know why I had the idea that was the last. High temperature and low pressure. Yeah? No, that's not. Okay, so this is a combination. Yeah? Okay, perfect. So we got exactly 24 degrees Celsius. That's what we were. After the equilibrium has been established, the total pressure inside is, the pressure is 0.709, oops, 0.709 0.709 atmosphere. That is the total pressure inside. Okay, it says, okay, some solid NH4S remains in the vessel. What is the Kp for the reaction? Well, the first thing is that you have to determine, right, Kp by looking at the products of the reactant. If you have the products here are the ammonia gas, H2S, okay, and dihydrogen sulfide and the solid. But you the solid you didn't put it in the equation equilibrium expression. So it would be a partial pressure. The partial pressure of Na3 multiplied by the partial pressure of H2S. And if you look at the equation, it's a coefficient of 1 each one. So that's the Kp. Now, how do we determine the Kp? We got here, okay, let's look at the equilibrium. If you got this in equilibrium, guess what? If you got 0 here, well, 0, this is a solid, sorry. You don't count it for the equilibrium. So this is gonna be, um, this was the solid initially, and then you got 0 and 0 of the gas. The change would be, and this is ICE. Okay, the change is a 1-to-1 plus x, right? And this would be x and x. So you know that the Kp is going to depend on the two gases, and this would be my x. So the Kp here on the left side, Kp, Kp is equal partial pressure of both gases. That would be x multiplied by x. Kp would be x to the square. Okay, so what do you do here? Do you have this value? The partial pressure? No. But you know they give you the total pressure. And the total pressure, if you remember, is 0. Here it is. The total pressure is 0.709. So that means that if you have the partial pressure, it's going to be the 0.709 divided by 2 because you have equal amount. So if you have equal amount of moles for each one, okay, x and x, if you look at the equilibrium table, I see that means that if you have a partial pressure, the partial pressure of each gas should be divided by 2 because you have the same. So this would be 0.709 divided by 2 equals 0.355 atmosphere. Okay. Now, let's do the next step. And it says the Kp. The Kp would be equal to 0.355, like I said, by 0.355. So that gives you a Kp of 0.126. And that's my first answer. The next one, the next one would be you got the next question is going to say, what percentage of solid has decomposed? Well, you have the initial mass, okay? You can do it even with moles because you can get a percentage, okay, by dividing the moles of moles of the of the solid had decomposed, right? Divided by the total moles initial of the sample. Okay, but how do you find the moles decomposed? Well, remember something. We got the partial pressure of this, partial pressure of this, and this is a 1-to-1 ratio. So you can know how much decompose. But as I said, this is partial pressure. How do you find the moles? By using the ideal gas equation. Okay? You know that the pressure of each one is 0.355 atmosphere. You know, of course, the constant, and you know that the volume is 4.0 liters. Okay? And the temperature, 24 degrees Celsius. So that tells you that we're gonna first find out the moles that decomposed that are coming from here, okay, which is X. And if you remember the partial pressure, which has the X here, was 0 that we got by dividing by 2, 0.355 atmosphere, okay. The volume was, okay, 4 liters, right? For volume was 4.000 liter. The temperature in Kelvin is 297.15 Kelvin. Okay? And we have the constant, like I said, use exactly the value, but I usually say that they give you on test, but I'm gonna give you this one. This is the one I use all the time. 821, okay, liter atmosphere moles Kelvin. Okay, so we got pressure. Okay, we got that the number of moles, okay, that's what we're gonna find out, okay, is equal to the pressure multiplied by the volume divided by RT. Okay, so that way we can find out the moles of each of these gases. So if we have either one is the same amount of moles. So you got N equals, what is the pressure? 0.355 atmosphere multiply by 4 liters, 4.0 liters, 400 liters divided by R 0. I'm almost finished. 0.0821 liter per atmosphere divided by mole per Kelvin. Okay, atmosphere, liters, oops, liters and liters cancels out. Right? Liters and liter cancels out, and you got that the number of moles, and I forgot to put the temperature here, and the temperature would be equal to multiply by 297, okay, 0.15 Kelvin, okay, Kelvin and Kelvin. So the number of moles, okay, that decomposed was 5.82 times 10 to the negative 2 moles. So now we can find out the percentage of sample that decompose. Why do we use grams? Why not using gram? Because we have it already in moles and the P. So now we're gonna do, okay, we need to find out the moles of the total moles. Where do we get it from? The total moles are coming from the sample, the grams of sample divided by the molar mass. Okay? And that is done already. That is done already. And uh, it's gonna be, hold on, I can find the answer for that. I did it already. Okay, divided by the molar mass, the number of moles initial of the solid, okay, would be equal to, here's the number of moles, um, 0.1205. 0.1205. Where do they get it from? 1205 moles. These are the moles of the solid divided by 6.1589 by the molar mass of this. So it's going to be, okay, the percentage is going to be the moles that we found out. That is going to be 5.82. Remember 582 over here. 582, the moles we found out for each gas. 582 by 10 to the negative 2. Okay? 582 times 10 to the negative 2 times 10 to the negative 2 moles. Okay? You divide it by the moles, the total moles, where it was 12.05, the moles of sample, and then you multiply by 100, that gives you the percentage, and it's gonna be the percentage finally 48.3%.